Hello, good evening to all. My name is Mohammed Sabir. Today I am here with you. In this sessions, we are going to start a electro discharge machining. Basically, what we will learn in this session, I think you can. This is screen is visible. I think this is screen is visible. This is a slide of electro discharge machining. What basically we will learn in the electro discharge machining. Basically, there are a lot of content content like we want to introduce first what we are going to deliver. The introductions, it consists introductions, history, a general aspect of EDM, component of subsystem, working principle, EDM setup, types, modeling, other. Like most of the time we will devote in modeling and simulations because this is very important, like how to model the EDM and how to find out the MRR. Okay, and look into the like this is the history of EDM, okay, like EDM is how EDM uh, is generated, then the history you can look into that. And now we go to the simple EDM process. What basically EDM? EDM is electrothermal non-traditional machining process, a series of rapidly recurring current discharge between two electrodes. What basically happens? Like in a EDM, we have a like first we want to give some a flavor of EDM. What basically happen in EDM? Like this is a setup of EDM. We have a tank, okay, and this is a workpiece, and this is a we have a tank. This is a workpiece, and over a workpiece we have to maintain a gap between electrode and workpiece. Like electrode, it's just like a tool, okay, and first thing is there like the gap is maintained by a servo control mechanism. The gap between workpiece and electrode, which is maintained by the servo control mechanism, and for to generate the electricity and to generate a pulsations, what we are using, basically we are using a rectifier control current control system. We will look in later like what type of system we are using for that for particular like RC circulation, and there are a lot of things, a lot of parameters, a lot of devices we are using for that. Okay, what basically we have, this is a dielectric fluid. Is basically a dielectric. 1 minute. First we connect there. Yes. What basically happen? This basically a dielectric. This is a dielectric fluid. This is a dielectric fluid, and this is a workpiece, and this is a uh, tool. Okay, what basically happens? You know, the workpiece, the tool, the tool is on a workpiece, and like uh, some gap should be maintained because in this gap sparking happens. Okay, what basically happens in this gap, like we will discuss in detail. What basically happen, like we have five things. Okay, we have five things. There are we can divide into the five things, and there will be five things. Okay, there are five things we can divide into, we can categorize into the EDM process into the five sub parameters. Okay, and this is simple things. What basically happens, like we have a tank and dielectric fluid workpiece, and the tool is on a workpiece, and like as we apply a electrical supply, and due to electrical supply sparking happens, and this thermal energy are converted into the this electric energy converted to thermal energy, and due to this thermal energy, evaporations happens and crater becomes. Okay, in detail, we will discuss in later. We'll discuss later like how uh, what physics behind it. Okay, this is a general aspect of EDM and where we use EDM to machine hard metals, and metals are electrically conductive and cut intricate contours or cavities and hard steels used in any other metals or metal, namely superalloys, and shape polycrystalline diamond tools. Okay, uh, here we are using a EDM process. Mainly EDM process is used to machine the hardened surfaces. Okay, the MRR depend on the thermal property rather than its strength. Okay, a geometry of tool will depend on a thermal properties of tool. Why? Basically, it does not depend on it does not depend on the strength of workpiece. The machinability does not depend on the strength of the workpiece, rather than it totally depends on the thermal strength and thermal properties of a system. Like the tolerance of like touch surface finish, and the data is given, and this is the basic EDM 5 component: power generator, servo control, servo system, the tool and tool holder, dielectric reservoir, and workpiece holder and device. Basically, the power generator where we store electrical power. The servo system is used to basically maintain a distance between workpiece and electrode. And the tool and tool holder, the basically tool and tool holder is basically a kind of electrode. And dielectric reservoir is a dielectric fluid which basically behaves as a uh, is basically responsible for to make a ionization channel. And workpiece holding device, this is this kind of CNC arrangement. Okay, and now we will go for the EDM components. You can say you can look into that. This chart is given, and this is a basic EDM working principle. Now we discuss that how this channel, like how this plasma become. Okay, how this plasma become, and like how what working principle, how it works, and what working principle behind it, what physics behind it. We are going to look into that. What basically happens, we have an electrode and this is a workpiece. Basically electrode is connected to a negatively charged and workpiece is connected to positively charged. Okay, and due to basically due to negative charge, what basically happen, electron which is bounded to the uh, nucleus get energy from a system, and like when this energy is more than the binding energy, basically it try to leave your space. And so what happen what happened basically, due to that electronic emissions happen from a electrons. Okay, this electron emissions, what basically these what electron, like these electrons from this electron emits, and this emission is called a primary emissions. Okay, in next uh, we simultaneously we are passing a dielectric fluid. Simultaneously we are passing the dielectric fluid. uh, in dielectric fluid, what basically happens, the positive negative charge, due to that electric field is generated. In this electric field, what basically happen, is accelerated in the direct electron is accelerated in the direction of positive, like towards the workpiece. Okay, because of that, it strike the workpiece and generate a thermal energy, and due to this thermal energy, uh, the workpiece evaporates and melts. But in in Adding to this cold emissions, what basically hot emissions is also there. Like how hot emissions is generated. You know what this dielectric we have a like flow of a dielectric medium. We have a flow of dielectric medium. The electron which is emitted through a electrode is basically collide with a uh, dielectric atom. Okay, what basically happened due to dielectric matter, due to this collisions on dielectric medium, basically break into the two ions. Is actually break down into the it basically break down to the two ion. First is ion, another is electron. What basically happen? You also can say the number of electron. Uh, Earlier we have a less number of electron, but now we have a more number of electron, and plus also a ion is also there. So the net amount of current which is passed through a positive negative will be will increase. And what basically happens, this due to this ionic moment, ionization channel becomes, and these because of that ionization channels, corresponding to a current is also there. And because of this electric energy converted into a thermal energy due to a striking to the workpiece and electrode. And these thermal energy is converted into a this electric energy is converted into a thermal energy, and workpiece evaporates, melt down, and crater becomes an like this is the basic working of EDM, electro discharge machining, like how machining will be done. Okay, this is the basic process. Okay, now we will go to the this is the EDM working principle. Now, okay, let's move ahead. Like we basically saw the working principle, EDM working principle of EDM. But now we will go to the basically how to model the EDM. Okay, like we have this setup VI characteristic of the electro discharge machining. Okay, we have it, and uh, this we have discussed these all things. This is schematic of the EDM process. This is the basic schematic of the EDM process. This is the basically a fishbone diagram of the EDM process. Miscellaneous tool, electrode, workpiece, a dielectric liquid, power supply, EDM process, performance on MRR, and surface roughness electrode wear. Okay, now we go to the modeling part of EDM process, like how EDM process, how to model the EDM process, like how we find the MRR of this process. Basically we have a two type of basically we can categorize into two types. One is the die sinking EDM, another is the wire cut EDM. In wire cut EDM, what basically happens in die sink EDM, what basically we have a like workpiece having a shape such that like such a cup shape. Okay, and we have an electrode which is basically uh, dipped into the workpiece, and some gap should be maintained. Okay, uh, why? Because we have to flow uh, dielectric fluid through this gap. Okay, and sparking spark energy is generated, and due to the sparking energy, what basically happens? Workpiece is evaporated. Workpiece is evaporated, and it basically melts down. Okay. In the wire idiom, what basically wire idiom? Basically, we have this kind of we have this kind of surface like we have this kind of surface. What basically we do, like this is a wire wire cut, this is a wire, and we have to maintain a gap between workpiece. We have to maintain a gap between workpiece and tool, like electron. And as we move ahead, the machining will be done. Okay, this kind of thing we have discussed. There's a hybrid wire cut EDM. You can control EDM power control circuit, power generator like rotary impulse type generator, resistance capacitance type generator, rotary impulse type generator, voltage and mechanical type, and resistance capacitance type fluctuation generator, electronic pulse generator, and hybrid EDM generator. Okay, these are the basic circuit, like how to generate a electrical supply. Pulsations. These are the important things. These are the important things. Now we go for the, like this is on off time, on off cycle. Like this is a basic kind of, the current is changing with time and voltage is also is changing with time. Okay, basically variable, like we use a variable current. We use a basically a supply having a variability of current and voltage. Now we analyze of RC reference circuit. What basically we have, RC circuit analysis. What basically we do. Simple. We have a, like, uh, the first circuit is for what? To store energy. To store energy in capacitor. Okay. And the second circuit is for what? Basically to generate a sparking energy and to emits, to basically to deliver energy to the, is basically used for what, is basically used for what, the energy which is stored to the capacitor is transmitted to the electrode, like electrode. Okay, whatever energy we have, we transfer to the system. The first is the V note is the open circuit voltage, and VC is the voltage across the capacitor. And the drift current. What is the formula of drift current? Drift current is what? C del V upon del T. Basically, I think you have learned in your earlier classes. A drift current is equal to is what? V naught. Basically, across this current, V naught minus VC upon RC. This is delta V upon R. Accordingly, you can write it. And when we use this formula, what basically happens, derive it, and we get this formula Vc is equal to V naught 1 minus e raised to power minus t upon Rc into C. Okay, this is a Vc, and by using it, we can find out the Ic. Ic is what? V naught minus Vc upon Rc is equal to I naught e raised to power minus t Rc into C. Okay, then we uh, we got the we get the IC and we see this is the basically instantaneous current across the capacitor and across the instantaneous voltage across the capacitor. Okay, and now we go to the how to find out the IDVC into RC minus C del VC upon del T TD. And this is what basically like initially voltage is, what is the voltage, like in a discharging circuit, what is the initial voltage? Basically, it equals to the charging voltage, which actually maximum charging voltage in a charging circuit. Okay, and VC dash to VD dash and GA to TD. Accordingly, we can find out the VD and ID. VD and ID, VD and ID, and is what VC into RM minus C del VC upon del T, and accordingly you can find out the VD star, which is also the is basically a VD star, and this discharging in the current approach. This is what VD into RM. This is instantaneous voltage and current in a discharging circuit. Okay, now you easily can visualize that the first charging circuit gains the capacitor gains a voltage up to VC star, and then the energy when in case of discharging the the lower voltage, which basically will be will gain by the will be gained by the capacitor is VD star. This is the breakdown voltage VD star. This is the maximum charging voltage VC star. Okay, and what basically happens after finding it, we you know that VC star is what is basically a 0.716 into V naught. It's basically a 70% of V naught. Okay, and by using that, like we see, like we basically want to find out the TC. TC is what basically like how much time will be taken by capacitor to discharge to charge. Okay, how to find it? Just TC, like basically VC is what V naught, VC is what VC star. By using them we can find out this TC, and accordingly we also can ID star VC into RM, and we also can find out ID, and accordingly you can find TD. This is a discharging time. Okay, and like total energy discharge through a spark gap, which is 0 to TD I square RM dt, is what basically we get a half VC square, which is this approximate value. Like what is the how much frequency of the system? Okay, like uh, for the frequency of the system, F is equal to 1 upon TTC plus TD. F, we get F is F. Like this is a basically we get a F model for the MRR, and now we come to the modeling part of. Okay, now we come to the modeling of the MRR and tool VR. First, what basically we do, MRR of medium profile is proportional to the half C VC square into frequency. VC is what VC is basically a maximum discharge charging voltage. Okay, and the frequency we can basically approximate this frequency value of frequency is such that take 1 upon RC into C ln V naught upon V naught minus VB. Okay, K half VC square, half CV square, half CV square 1 upon RCC ln V naught minus VB. Here V naught is what open circuit voltage and VB star what discharging voltage, breakdown voltage. Like you can see this, this kind of MRI. And model 2, what basically happens, we basically assume that key 2 by 3 pi r cube, like the hemisphere of the crater is proportional to the what basically happens, like vi into t on. Vi is the corresponding power, and when whatever t on, we get a sparking energy. Okay, energy of single spark, this proportional to k into es is give the available energy, because k is the some error factor and this material removal in a single spark would be proportional to the spark energy. Like this material removal in the single spark would be proportional to the spark energy is what is proportional to the g into es. G into es, like how we can estimate that EWS K into ES is this this is the G into ES. And you know what is the MRR? MRR is what? Tau upon TC. Here tau we can write it G into EC, G into EC, and G into VIT on, G into VIT on, and you also can write T on plus T off. Accordingly you can find out. It's so simple, not tough. Okay, recap. It's not tough. Okay, like how to this is the basically a modeling of like how you can, like how you will remember this. Okay, like first what basically this is the half meter here. 2 by 3 pi r cube is the volume of hemisphere of the crater. Okay, and what basically, like this the tau is what? G into es. MRI is what? The volume, crater volume upon TC. In the crater volume is proportional to the ES. Okay, sparking energy VIT on G into VIT on, G into VIT on, T on off, T off. Or you can also write it. Okay, and modeling of roughness. Okay, like how to, when we do the processing by EDM process, like we oh, we also interested to find out like how much surface, like modeling of surface roughness is EDM. Okay, like what basically you can see, like when we go to the EDM process, we also interested to find out the surface roughness. Okay, surface roughness is proportional to the crater depth upon frequency. 2 by 3 pi r cube is proportional to half cv square, and here we get a r is what? R is what? Half cv square by 2 by 3, because the crater, the crater volume is proportional to the sparking energy, and accordingly we can find r is what? K for a crater depth r, half cv square 2 by 3 raised to power 2 by 3 and into 1 by f. Accordingly we can find out. Please remember it कि RA is proportional to the crater depth upon a frequency. Crater depth upon a frequency. Okay. 2 by 3 pi r cube proportional to the half cv square. RA is what? K for half cv square raised to power 1 by 3 into 1 by f. F is equal to 1 upon Tc plus Td, and we get the discharging time so small that we can neglect it. We get this formula. R is crater depth into. Okay, and modeling of surface roughness according to model 2. This is the HMR, 2 by 3 pi r cube. R is what? 3 by 2, 3 by 2 sigma, so sigma GES and G VIT on. So accordingly we can also write it VIT on upon 1 by 3, VIT on by 1 by 3, 1 by f. Okay, and here g and k3 are the constant. Okay, now the next remaining part we will do in your next sessions. Okay, thank you, all the best.